I'll be talking about MatrixNet, which is our main tool at Yandex for machine learning. I work as a chief data scientist at Yandex Data Factory, so I'll start with a few words about what that is. So it is a kind of internal startup which was open last year, and the goal is to apply our assets such as machine learning infrastructure, computing resources, and data scientists to solve problems of other companies in other industries, such as, for example, banking or telecom industry, or even federal road agencies. And in doing our projects, we use MatrixNet heavily, and I will also give you an example of such projects for outside companies. So now, what is MatrixNet? Basically, it is our internal implementation of gradient boosting over decision trees by Andrei Gulin in the first place. He will be telling you more about his research later today. But it has a lot of useful features. So MatrixNet provides different modes for classification, regression, and ranking, obviously, and also some combined objectives can also be used, and some of them are already implemented, and it can be implemented some custom objectives if you need it in your problems. And one of the key features is that basically MatrixNet was initially trained in a kind of meta-learning fashion when we took a lot of data sets and tried to optimize all of the parameters in the first place, so that when you apply it to a new problem, you really don't have to fit parameters. And really, that worked out. So you basically get very strong results with default parameters, which beat most of the tools we know outside, which are publicly available in the open source. And you almost don't have to fit any parameters when you use it. And that's one of the reasons it's easy to use. So it's really not only an easy tool for software engineers. For example, managers can use MatrixNet to solve problems, or just to find first approaches to some problems. And we even have an internal web interface called Friendly Machine Learning, where you basically only need to upload a pool with features and the target value, and specify what you want to do, like classification or regression or ranking, and then it just works. So you don't have to really know how it works to use it. And you don't need to do things like feature normalization, which are standard for some other algorithms. So here, it just does everything for you. Obviously, it's also highly optimized because you know, at Yandex we have web services for which we can see requests per second on the order of tens of thousands per second. And so, and for some of them, like search or search ads, you have to apply MatrixNet thousands of times for each such request. So it has to be really optimized to serve all that level of workload. And it uses both algorithmical optimizations and also a lot of low-level optimizations. But also training is crucial. Training time is crucial to the number of experiments which you can do. And we're doing like thousands of experiments each year. So to do those experiments with training on large pools, you can both train locally on your machine, or you can parallelize it to run on a huge cluster, and it can scale with a number of machines pretty well. So some of the MatrixNet applications at Yandex include, obviously, the first and the main is web search ranking, for which it was implemented in the first place, but also ads click prediction and some external projects of YDF, and these I will tell you about. Also recommendations, which Michael Rosner told you about previously, and actually a lot of others, like bot detection, resolving homonymy and other natural language processing, user segmentation, and many, many others. So let's start with some tricks and features of MatrixNet. So why does it work so well? So one of the first things that distinguishes it from different other implementations is oblivious trees. So what is that? So you see, usual decision tree consists of several layers which can be different, and the conditions in each node on each level can be different. So for example, here is f2 more than 3, here it can be different feature with a different threshold. as opposed to oblivious trees, where the tree is always fully balanced, and the condition in each node on each level is the same. So basically, we divide the space not in such restricted rectangles in the 2D case, but we always divide the space from one end to the other. And this is both a means of optimization for application of such trees, but also is a means of regularization of your classifier. And we found out that in practice this works really well. So one other important thing is leaf regularization. So one of the common things when you implement things like decision trees or random forest or gradient boosting is that when you have a tree, sometimes you grow it, and at some point there are too few objects in your leaf. And so the question is what to do with that. And usually what people do is just don't grow the leaf if too few objects are there. Or after you've built the tree, you just prune it by deleting some nodes. What we found out is that first, we cannot do it with oblivious trees, obviously, because they have to be full binary trees. But from the other hand, we found out that instead of limiting the number of objects in the leaf, we can regularize the leaf if the number of objects in it is small. So basically, depending on how many objects are there in the final tree in this leaf, we can regularize the value from this leaf with some confidence function, which depends on the number of objects. And we've played a lot with different variants of this regularization function. But basically, in the end, we found one which works really well, and we think this regularization even can beat other ways of regularizing big trees. And third important thing is that we try to gradually increase model complexity. So usually when you do like random forest, for example, you build each tree completely separately, you build it up to the end, and then they're randomized, and that's why on average they work better. But what we want to do is to regularize on each step so that we are really safe from overfitting. And we do that by first building trees of only one level. And then after some number of iterations, when it is already doesn't give any improvement, we do 2 levels, 3 levels, and so on. And usually, in most cases, up to 6 levels works for us really well. We don't do trees deeper than that. So some of the features include that really in this implementation, it's easy to implement your own objective. And basically, to do that, you just need to implement the objective function itself and its gradient. And already implemented are things like mean square error or log loss. But also there are some combinations of losses. For example, ranking and classification losses can be combined. And I'll tell you an example of application of that. And some non-standard metrics for ranking. So one of the other important things is we do feature binarization in the start. That means that we work both with the numeric and categorical features, but in any case, feature is divided into several buckets before we even start learning. It depends on the data set, obviously, but we do several heuristics algorithms to divide feature optimally into several buckets, like divide by value in relatively equal buckets, or divide by the number of objects into relatively equal buckets. And by combining those heuristics like that, we found a way which seems to be optimal. So what it gives us, again, is both an optimization when you train and when you apply the model. And this is a kind of regularization of your model. So you don't need to find a new feature binarization for each new tree. And that is kind of regularization, which works well in practice. And also, one of the features of MatrixNet is at the end, it gives you an output of how important are different features and from different angles. So one of the angles is how much did this feature influence the output of the classifiers, the value that it predicts. And this just gives you the features which are frequent and which are very important. But also, when we work, for example, in search, there are like many hundreds of features that are not that frequent, not that important in total. But when you sum them up, they are very important. So you need to estimate how important that feature is also. And there is another measure which is called efficiency, which basically estimates in the cases when the feature was even activated, how much did that influence the answer. So then you can see not only features which are always important, but also the features which are important in a small region of space where they're really important to your algorithm. And also you can estimate your correlations between pairs of features and the target, which is very useful to work on improvement of your algorithm or even find bugs in your input features. So now to some of the applications. Ranking is the first application. Basically, the first usual thing is we train on judged query document pairs. Actually, usually we also include a region in that triple, but for simplicity, I assume just these pairs. And judgments are, for example, these 5 classes, which are standard. And we use different features like per query, per document, query and document combined. And also you can use features of URL. For example, it could contain some parts of your query in the URL. And you can think of how your host is authoritative or not, and about link features to find out spammers and things like that. So there are different settings to solve the problem. For example, you can do it with multi-classification, and objective is cross-entropy, which is readily available in MatrixNet. It's not very good because this way you lose information about order of those judgments even before you start training. Another way you can do regression. For example, excellent is 1, good is 0, and then the others are somewhere in the middle. And you can do objective mean square error. That is also readily available. That can be also not that good. Actually, usually people use some ranking objective because you don't really need to exactly approximate those numbers, which are a little bit arbitrary, which you assign to different marks. But what you need is good ranking. So now how to optimize ranking? Well, NDCG is non-smooth. So in this case, there is no gradient to do gradient boosting. So what we need to do is to somehow approximate it with a smooth ranking objective. And one of the ways to do that is, for example, to specify a probabilistic distribution on permutations, which give bigger probabilities to permutations which rank documents more correctly, which rank good documents higher. And then your expected NDCG, for example, can be already smooth, and you can optimize it with gradient boosting. Or alternatively, you can use a pairwise approach. So basically, you can ask your judges to just compare pairs of documents for a single query, and then estimate the probability that one of them is better than another. And that can be done basically with a kind of log loss. And then you maximize likelihood of data given the predictions. So this is one example. Another is ads click prediction. So we're talking about search ads. And when user enters a query or clicks a link, advertisers enter keywords. And then when user enters a query, we need to match it with keywords, which advertisers specified, which describe their ads. And then we need to show the best ads. But the problem is which are the best. There are like, for each query, there are like thousands or maybe hundreds of thousands of matching ads. And we need to select on the order of 1 to 5 best ads to show. So basically, the principle is that we need to show relevant ads which maximize revenue. And expected money is obviously probability of click multiplied by something like bid in the auction. Not exactly that, but approximately. And actually, what we need to improve is also relevance. Because if we just show the most money-making ads, users will be not happy. And advertisers will also be not happy because after clicking, they won't buy anything. So we actually need to make ads relevant to the search query. So this can be some formula like this. The key thing is that we need to find probabilities very precisely. So to do that, the usual solution is to use log loss, because it just gives you, after a sigmoid transformation, probabilities. And then you can maximize likelihood of your previous click data given the predictions. But there's a problem with this approach, that if your ranking doesn't change, even if you improved your binary classification model and its log loss went up like 5%, but the ranking doesn't change, then it didn't actually change your system. So it's not good. And what you really need to do is to give the best possible ranking. And turns out that ranking objectives can work better in solving this problem than binary classification. So in practice, what we do is we use a combined objective, which is also one of the features you can use in MatrixNet, combined objective of both classification and ranking, and then tune between them. So another example is an external project of YDF. So at first we thought that it could be beneficial to use our machine learning infrastructure to other companies' problems, but we're not sure if they're really superior to other approaches. So this is one of the examples we had. So telecom companies have this problem of users which are going to other telecom companies, and they want to save them because there are no new users of mobile phones. You need to save your user base, and they need to predict which users are going to switch next week. Why next week? Because during this week they have enough time to prepare a campaign for prevention of switching, to give you some discount or to talk with you and convince you to stay. So what we did is we built another model for this churn prediction. This is called churn when they switch. And we compared it with the in-house telecom model with a standard industry metric of lift 10%, which means basically how much times more is the concentration of churning users in the top 10% predicted by your model than in a random sample of 10%. So this is like a historical metric used in telecom industry. And we compared with the in-house model on the same data with the same features. We didn't have access to any raw logs of user activity. We just had the data set prepared by them. We could, of course, make feature engineering over that, and we did a little of that. But basically, we had the same data set and needed to predict the same thing. And I can mention that they were working on this problem for decades. So we won on cross-validation at first by 18%, almost 19, and then by 11.5 on test data. And the difference here is not because the model was incorrect. It's actually because between the training period and testing period, there were like several months. And then the churn rate of that operator grew 2 times almost during that period. So you can't really compare these two numbers between themselves. But anyway, more than 10% is a huge improvement over some problem which people were focusing on for many years. And the key point here is that most of this delta was not like feature engineering or parameter fitting or something else. Basically, 90% of this delta we get with the first application of MatrixNet. And then we did some feature engineering and some parameter fitting. But already 90% of the result was by then. So about some MatrixNet limitations. So it doesn't work really well with multiple category features when the feature is not ordered in any way, like a region or a zip code. And there are a lot of values of it. Because of the binarization, it tries to do buckets of different feature values, but if the feature is not ordered, there is no meaningful way to do that. And to deal with that, you need to apply external improvements, such as, for example, bin counting. And I think Misha Belenka was telling yesterday about some of those techniques. So also sparse features like text or some others which are not even categorical, but you want to use them. To use such things, you can, for example, build a separate linear model and then input it as a feature to MatrixNet, which is what we do usually. Or you can do word embedding and then do a linear model on that. And basically, in production, we always have MatrixNet as the final step, but we can do stacking of models which provide features for MatrixNet there. Also, one of the things, because of binarization, you cannot divide discretized features, so you have to divide them manually. If you need some CTR, you probably should just compute it. And also, there are things like continuous dependency of result on the features and some golden feature, which is so good that it's almost the answer. And in both these cases, binarization doesn't help. So basically, one of the ways is increase the discretization of all the features. Another way is just first build some continuous model, like linear model, and then build a MatrixNet model on the deltas from that model, and that works better. So some conclusions that MatrixNet is our implementation of gradient boosting over decision trees with some bells and whistles, handles well both numerical and categorical features, and almost no tuning is needed. Basically, you only need to think about your features. Training is parallelized for huge clusters and optimized, as well as application, and is often superior in practice to all other models that we've seen. But of course, some careful feature preparation is needed because of the limitations I told you. So if you want to get even better results, you need to understand the algorithm really well. That's all. Thank you.
Thank you. If you have any questions to Michael, please feel free to ask.
Thank you for your report. There is a maybe silly question, but it's not obvious for me. If MatrixNet is so cool and better than other implementations, why are you still keeping it closed sourced for so long period?
Well,
it's cool to know, but outside of Yandex, it's most useless.
Yeah, there are two answers to that question. I expect that question. So one of the answers is that, as you see, we're trying to build a startup based in part on MatrixNet and some improvements over it, which we also have internally. So that's why we keep it closed sourced. The other answer is that Andre here is working with CERN, and they do a project called Reproducible Experiment Platform, where MatrixNet can be included. And for physicists of CERN, for example, we give some limited access to MatrixNet. So it could be a limited access to some scientists. And probably if you want that, you can talk to Andre, and you can discuss if that's possible.
OK, thank you.
So I'd like to understand the oblivious trees. It seems counterintuitive to me that you force the splitting, you force the tree to be complete because the various regions underneath the tree would have less statistical significance for each region. So can you explain the motivation of oblivious trees versus regular trees?
So the main motivation is basically that it is a kind of optimization, but turning about different regions with different sparsity. We solve that problem by regularizing. So when you have a leaf with only a few objects in it, we apply a multiplicator, which is small when number of objects is small, and which grows up to 1 when the number of objects approaches infinity. So basically, you both do a regularization, and your algorithm works faster. And then we've played with a lot of different types of regularization in the leaves. And we've basically found in practice the one way that works well. And unfortunately, there's no like scientific explanation of why that works, but it's like an empirical approach.
Time for the last question.
Thank you. How do you compare MatrixNet to XGBoost?
Yeah, we've compared MatrixNet with XGBoost. What we found is usually basically twins by several % of quality, and also in XGBoost you can do as good, but you need a lot of parameter tuning to reach that level. While in MatrixNet, basically the first launch already gives you the same result. So that's I mean, we didn't have like a lot of experience, but of course we compare it and. Looks like you have to do a lot of tuning. But otherwise, XGBoost is probably one of the best we've tried outside.
Okay, thank you very much. Let's thank Michael once again.